Today we are going to learn some basic things about cyclohexane. First, let's learn how to properly draw the most stable chair conformation with its hydrogens or its substituents. First step would be to draw two parallel lines slightly tilted. Then, another two parallel lines that start from the ends of the previous lines here and here. And to finish the cyclohexane, another two parallel lines that will connect the existing formation. Now let's place hydrogens in proper positions. This is very important. Please remember, there is only one correct position for each of the substituents. Now let's do the easier part first. Vertical hydrogens are called axial and they are alternating up and down. I usually start with the right upper corner of the chair conformation and then I add substituents. First vertical up, then vertical down. Vertical up, vertical down, finally vertical up and then vertical down. Next step is to place equatorial hydrogens on a chair conformation, and those are in a horizontal, or I should say almost horizontal position. This is important. On a carbon number 1, we place a substituent in such a way that this line is parallel to the side of a cyclohexane opposite to it. Here on carbon number 2, parallel to this side. On carbon number 3, substituent is parallel to this side across from it. On carbon number 4, substituent is parallel to this side. On number 5, parallel to this side. And finally, on carbon number 6, parallel to this side across. At this point, we can add hydrogen atoms in place of substituents. There is overall 12 hydrogen atoms, 6 in equatorial and 6 in axial position. Now we can learn how to flip the chair. As said earlier, chair-to-chair flip happens really fast as barrier for that process is very low. The two chair conformations are the most stable conformations of the cyclohexane and therefore lowest in energy. So, how to go from one chair into another? We will use this example and we will learn how to properly draw the second chair conformation when given the first one. On a picture, carbons number 2, 3, 5 and 6 are all in one plane, but carbon number 1 is above the plane or nose up. Carbon number 4 is below the plane or nose down. When flipping the chair, we keep carbons 2, 3, 5 and 6 in one plane, but carbon that was above the plane will go below the plane and carbon that was below the plane will go above the plane. So I will redraw the first chair with its substituents. I will do so the same way we did before. When showing the other chair conformation, we have to show carbon number 1 below the plane and carbon number 4 above the plane. Remember how we started drawing the chair conformation with two lines tilted to the right. In this case, we will start with two lines tilted to the left. Then continue the same way as we did before. From those ends, we will draw two parallel lines, one from end here and the other from end there. To finish the chair conformation, we will connect the ends to complete the structure. I always start with carbon number 1 on the right upper corner. Now, in our flip chair conformation, the carbon is below the plane and carbon number 4 is above the plane. But we have to add our substituent. On position 1, substituent was in axial position, but after flipping the chair, it will go in equatorial position. On position number 3, substituent was equatorial position, and after flipping the chair, it will become in axial position. We will show this on a model as well. It is very important to learn how to identify a molecule as cis or trans when we are talking about the chair conformation of cyclohexane. We can only talk about cis or trans cyclohexane if we have two substituents on a molecule. So what are we looking at when identifying the positions? Please remember, we are not looking at axial or equatorial position, but rather if the substituent is up or down. Let's take a look at the first example. Before that, let's properly draw in the hydrogens on positions 1 and 4 so that we can determine what is pointing up or down. On position 1, methyl group is up because hydrogen is pointing down. On position 4, methyl group is up again because hydrogen is down. Both groups are up, meaning on the same side of the molecule, and therefore this molecule is cis. The full name for this molecule would be cis-1,4-dimethyl cyclohexane. Common mistake here is that students identify methyl group on position 1 as equatorial and methyl group on position 4 as axial, and wrongly name it as trans because one group is axial and the other equatorial. Please remember, when naming the molecule as cis or trans, we need to identify substituents as up or down and not axial or equatorial. Let's do another example. On position 1, methyl group is pointing down as hydrogen on the same carbon is pointing up. Methyl group on position 3 is pointing up as hydrogen is down. Substituents are therefore in the trans arrangement with respect to each other. The full name for this molecule would be trans-1,3-dimethyl cyclohexane. Fun fact: diamond is a network of infinite cyclohexane rings. Namely, carbons are covalently attached to each other, producing a three-dimensional structure. Diamond has no free electrons and it doesn't conduct electricity. It is also the hardest material known and is used for cutting and drilling. Formula for both graphite and diamond is C. Diamond and graphite are both allotropes of carbon. Allotropes represent different arrangements of atoms, and due to this different arrangement of atoms within the structure, physical properties are different as well. Graphite is also made of carbon exclusively, but from hexagons that are connected to each other and forming layers. Each carbon has 3 bonds to other carbons and a free electron. Those electrons are delocalized, and this is why graphite is a good conductor of electricity. Also, completely opposite from diamond, graphite is very soft. Between the layers of graphite, there are only weak intermolecular interactions, and this is why those layers easily slip. Another allotrope of carbon is buckyball. This spherical molecule has a formula C60 and is consisted of hexagons and pentagons, and similarly to graphite, has delocalized pi electrons. This picture also represents a three-dimensional structure of a diamond. We already said diamond is infinite network of cyclohexane rings. Your homework is to find and label all cyclohexanes that you can see on this picture.